Hey everyone, and welcome back to this class, Advanced Convolutional Neural Networks. In the previous lecture, I taught you about the architecture of VGG. Now you might be wondering, this is pretty much the same thing as the LeNet, except you have more convolutions and more dense layers. So what's the point, you might say? I already know how to build that from your last course, you might say. And of course, that is true. So has the lazy programmer just conned you into learning about something you actually already learned? Well, of course, the answer to that is no. You'll notice that in my course descriptions, I always have this little blurb that the course isn't just about how to use the models, it's about how they work. Part of understanding how they work is first understanding the underlying theory, and then building the model based on that theory and using it on data. So using the model is always the final and most trivial part. Except for VGG, this is a little different. Yes, we know how to build it, and once we build it, we know how to train it and use it to make predictions. That's just two lines of code, .fit and .predict. So in a trivial sense, sure, we already know how to use VGG. But do we really know how to use VGG? That's what we'll be discussing. But first, what is a major pain point when it comes to this approach? Well, you may have noticed that the bigger your neural network gets, the longer it takes to train. In the past, we looked at models with maybe 3 to 5 layers. Sometimes that would take hours or days to train. And of course, the more data you have, that's going to multiply your time. Data itself is growing exponentially. In terms of development time, or in other words, the time you spend as a developer creating a system to perform some task, waiting for a neural network to train makes a big impact. Is there a way we could maybe shorten overall development time? Of course, the answer to this is yes. Luckily, we live in an age where the idea of open source is very popular. Researchers are much more open nowadays, and it benefits everyone. So instead of having journal papers with barely any detail that make things impossible to reproduce, we now have the exact opposite. Authors of journal papers often host their code on GitHub. The papers themselves are no longer hidden behind paywalls. Papers are usually first published on arXiv, which is totally free. But most importantly, developers often contribute pre-trained neural network weights for you to use. In other words, you don't have to train anything. You spend 0 time training. And not only that, but you benefit from the author's expertise and intuition about finding hyperparameters and optimizing the training process. That's not to say you couldn't find better weights, but you already know that the pre-trained weights that have been found have been proven to work well in the past. Okay, so other than the fact that you now don't have to spend any time training, why are pre-trained weights good? Well, you can imagine some scenarios where having pre-trained weights wouldn't work at all. For example, suppose I'm using one of my favorite datasets, some e-commerce data. So I have some input features like how much time the user spent on my site, which products they looked at, what website they came from, and so on. Well, pre-trained weights wouldn't be feasible in this case because nobody's data looks like mine. Only I have data from my website. So it's not possible for there to exist any pre-trained weights for this task, which is to optimize my personal website. However, images are different. An image is an image, no matter where it came from. As I always say, images and text are very special types of data. Sometimes people call this unstructured data, but I'm not a fan of this name because there is clearly structure in this data. Images are images, no matter where they came from. Text is text, no matter where it comes from. So for example, if I take a picture with my iPhone, it's going to have the same structure as a picture I take with my Android phone. It's going to have the same structure as a picture you take with your digital camera. A tree or a bush is going to be a green object, no matter what device you used to take the image. We have the same generality with text. The structure of the English language is the same, whether it's on Wikipedia or WikiLeaks. English is English. Nobody invents their own kind of English. Well, actually, sometimes they do, in which case, a pre-trained model wouldn't work on that sort of weird English. So what does this mean in terms of actual code? One of the easiest Python libraries to use when it comes to pre-trained models is Keras. Keras makes it super duper easy for you to download and use these models. Luckily, Keras supports both TensorFlow and Theano on its backend, so there's not much for you to do in terms of installation if you've already been taking my courses. In fact, we've already covered how to use Keras in a previous course. If you haven't seen Keras yet, I wouldn't worry too much because it is so easy to use, you can probably pick it up in a few minutes. So here's some code for using VGG and Keras. Just look at how simple this is. As many lines of code as scikit-learn minus the training part, because it's already been pre-built. One line to create the model, one line to make predictions. What's cool is that Keras comes with a lot of other pre-built models too. So on top of VGG, you get other advanced models like ResNet and Inception, which we'll be looking at later in this class. Now you might be thinking, okay, who cares? I could have done that myself. How is it possible to have an entire section in your course on advanced CNNs about this topic? And of course, I just told you that I don't make courses about how to use 2 lines of code, because I know all of you can do that by yourselves. So if we're going to build something here, what exactly is it? That is the topic of the next lecture.